Welcome to AI Paperslop. For you ML engineers and researchers tuning in today, we are jumping straight into a paper that honestly fundamentally challenges the current meta in zero-shot text-to-speech.
Yeah, it really does.
We're doing a deep dive into WavTTS towards high-quality zero-shot TTS via direct raw waveform modeling. And this is coming from researchers at ByteDance Seed in Shanghai Jiaotong University.
And the core insight you need to know immediately right up front is this. For years, the dominant paradigm for zero-shot text-to-speech has relied on lossy intermediate representations.
Right, like VAE latents.
Exactly, VAE latents or, mel-spectrograms, which are then paired with pre-trained vocoders to actually generate the sound. But WaveTTS throws that entire cascaded pipeline out the window.
Just completely gets rid of it.
Yeah. It is the first raw waveform generative TTS model that completely closes the quality gap with those latent space models.
Which is a huge claim.
It is. And by utilizing flow matching with a diffusion transformer, a very specific non-overlapping patchification strategy, an X prediction objective, and honestly a total redesign of how noise is scheduled, WaveTTS proves you can generate state-of-the-art speech directly in the uncompressed waveform space.
Completely eliminating all the cascaded errors you usually get from two-stage pipelines.
Exactly.
So now that we have the mission statement of what WaveTTS actually achieves, we really need to spend some time looking at why the field desperately needed this intervention.
Yeah, it's a good place to start.
Because if you look at the current generative TTS meta, basically most non-autoregressive models being deployed right now, they almost all operate in compressed continuous spaces. They avoid raw audio like the plague.
They do, and that avoidance introduces a massive amount of technical debt. I mean, let's look at mel-spectrograms, for instance.
Okay.
When you use a mel-spectrogram, you are explicitly discarding phase information and high-frequency details. You just toss them out to make the sequence modeling computationally tractable for the neural network.
Right. You are literally tossing out the exact timing of the sound waves.
Exactly. And if you use V80 latents instead, you are taking a highly complex acoustic signal and forcing it through an information bottleneck. You compress the data heavily.
Which introduces its own problems.
Yeah, because in both of those cases, these representations are inherently mathematically lossy. That immediately creates a hard upper bound on your generation quality.
Because you literally cannot generate fine acoustic details that your underlying representation has structurally deleted before the model even gets to work. I mean, the information simply doesn't exist anymore.
Right, that is the fundamental roadblock. And because your model's output is this highly compressed abstract feature space, you are forced to rely on a secondary system.
The vocoder.
Yep. You need a pre-trained vocoder like Hi-Fi Jam or a separate decoder to translate those abstract features back into something a speaker can actually play.
So now you've got a two-stage training paradigm.
Which is super fragile. Consider what happens if your diffusion model makes a slight prediction error. Right. Maybe generating a slightly blurry patch in the mel-spectrogram space.
The vocoder doesn't know how to handle it.
Exactly. The vocoder was likely trained on perfect ground truth mel-spectrograms. When it receives that blurry, imperfect generation, it doesn't know what to do with it. It amplifies the error.
Leading to those accumulation errors we hear all the time.
Yeah, the metallic decoding artifacts, the robotic sounding voices. It's just an incredibly inefficient way to map text to sound.
I always think of this two-stage process like photography.
Ooh, yeah.
Yeah, the current TTS pipeline is essentially taking a massive, uncompressed raw photo from a DSLR camera, compressing it down to a heavily artifacted JPEG just so your editing software doesn't crash.
That's a great analogy.
Right. You make your edits on that compressed image, and then you use a secondary AI tool to hallucinate what those original high-resolution pixels were supposed to look like before you destroy them.
Which is just making life so much harder than it needs to be.
It forces the obvious question, right? Why not just do the math on the raw file from the very beginning?
Well, because doing the math on the raw file has historically been computationally brutal.
Just way too expensive.
Yeah, raw audio possesses an incredibly high temporal resolution that neural networks really struggle to process efficiently. If you are working at a standard 16 kilohertz sample rate, which is standard for speech, that means you have 16,000 individual discrete data points for every single second of audio.
That is a massive sequence life.
It is. And to generate coherent speech, a model has to capture long-range linguistic dependencies. It has to understand the intonation of a sentence over, 5 or 6 seconds.
Right, the prosody.
Exactly. But simultaneously, it has to preserve microscopic phase, periodicity, and high-frequency structures at the millisecond level.
So trying to maintain global structure over tens of thousands of steps while perfecting the microscopic details in a high-dimensional continuous space.
Hmm.
I mean, that is basically a nightmare for sequence models.
A total nightmare. Which is exactly why older autoregressive models that tried to model raw audio, like the original WaveNet, were prohibitively slow to deploy.
Yeah, WaveNet is a great historical example here. It proved raw waveform generation was theoretically possible, but it auto-regressively predicted audio one single sample at a time.
Right, step by step.
So to generate 1 second of 16 kilohertz audio, the model had to do a full forward pass 16,000 times sequentially. You literally cannot parallelize that.
You can't. The inference latency made it entirely impractical for real-world zero-shot TTS at scale. So the entire field pivoted to latent spaces and vocoders, not because it was better for audio quality, but purely out of computational necessity.
Which sets the stage perfectly for what ByteDance and Shanghai Jiao Tong University actually built here.
Yes.
We need to look at the mechanics of the WaveTTS architecture.
Yeah.
How do they manage to ingest and process a massive, high-dimensional raw audio stream without immediately choking the compute, like WaveNet did?
So they tackled the sequence length problem with a highly efficient patchification strategy.
Okay, how does that work?
They take the 1D raw waveform, which they've resampled to 16 kilohertz, and they just slice it into non-overlapping blocks or patches of length 160.
Wait, so instead of a neural network trying to process 16,000 discrete samples every second, they are packing 160 samples into a single token.
Exactly. That simple grouping operation drops the sequence rate down to a highly manageable 100 hertz.
Oh, wow. That's a massive reduction.
It really is. Suddenly, a 10-second audio clip isn't an overwhelming 160,000 steps for the model to attend to. It's just 1,000 patches.
Which is well within the context window of modern transformers.
Exactly. This sequence length is short enough that a standard diffusion transformer or DIT backbone can process it efficiently using self-attention. They embed these audio patches and process them alongside text conditions.
Right, the text that you actually want the model to say.
Yeah. The text is encoded by convex V2 blocks, and they actually pad the text sequence to match the exact length of the audio patches.
Oh, that's clever.
It is, because this allows the model to learn an implicit text-audio alignment during training, entirely removing the need for external duration predictors that older models relied on.
Okay, so grouping the sequence into patches solves the memory bottleneck. But applying standard flow matching to this space raises a massive red flag for me.
Let's hear it.
Flow matching, mathematically, is about matching vector fields. You are predicting the velocity, right, the trajectory from pure noise to the clean data.
Right.
But if you are calculating that trajectory on raw audio, predicting the noise or velocity seems incredibly unstable when you hit silent or low-energy intervals. And human speech has a massive amount of structural silence, pauses between words, breathing date.
Your intuition is pointing straight at the reason why previous attempts at this have failed.
Well, so's a problem.
A huge one. If you use standard V prediction, where the network regresses the velocity field, predicting the difference between the clean data and the noise, the model is forced to fit a target that explicitly contains the stochastic noise component.
Because it's calculating the delta.
Yes. And in the high-dimensional waveform space, especially during those silent segments between words, or in low-energy frequency regions, the target becomes completely dominated by the noise itself.
There's virtually no actual signal to guide the gradients.
Exactly. There's no signal. The model is essentially trying to learn the specific pattern of random static, which means the gradients are going to go completely crazy during optimization.
It just leads to highly unstable divergent training. So how do they get around that?
To bypass this, the researchers implemented a critical mathematical pivot. They call it the X-prediction formulation.
X-prediction, okay.
Yeah, instead of predicting the vector field or the velocity, the network is trained to directly regress the clean waveform itself.
Whoa, wow.
Right. The model takes the noisy state at a given time step, and the neural network is explicitly asked to just output the clean ground truth data by 1.
So it ignores the path and just points directly to the destination.
Exactly. It bypasses the need to fit that stochastic noise target entirely. Mathematically, you can equivalently transform the original flow matching objective into this X-prediction objective.
And I imagine that stabilizes things significantly.
Massively. The beauty of this approach is that it drastically stabilizes the optimization in those noise-dominated audio segments. Even when the input is 99% noise during a silent pause in speech, the target the network is trying to hit is always the highly structured, clean waveform.
That architectural pivot is brilliant. But reading through the methodology, it's clear that changing the architecture and the objective function wasn't enough to make raw waveform generation work, right?
No, not even close.
Because we have to discuss the data-level physics of raw audio. The researchers uncovered a massive-scale mismatch that has historically broken raw waveform diffusion models before they even get off the ground.
Yeah, this specific discovery is arguably one of the most fascinating contributions of the entire paper. It all comes down to a concept called signal-noise variance alignment.
Break that down for us.
Sure. In a standard rectified flow setup, the kind we use all the time in image generation, there is an implicit mathematical assumption that your target data and your noise prior have comparable scales.
Right.
Usually, the framework assumes a unit Gaussian noise prior, meaning the standard deviation of the noise is 1.
Which works perfectly fine for latent diffusion models because you can just normalize your latent space to have a standard deviation of 1.
Exactly. But raw audio completely violates this fundamental assumption.
How so?
Well, yes, raw audio is technically bounded between -1 and +1, but its empirical standard deviation is actually tiny. When the researchers analyzed the 100,000-hour Amelia dataset, they found the standard deviation of the actual waveform data was only about 0.12.
0.12, that's incredibly low.
It is, and this incredibly low variance is due to all those microsilences, the natural pauses between words, and just the wide dynamic range of human speech.
Let me visualize this for you, listeners, because the math translates to a very physical reality here. Imagine the unit Gaussian noise prior is screaming at a volume of 1.0, and the actual speech signal you want the model to learn is whispering at a volume of 0.12.
That's exactly what's happening.
So if you don't correct for this mismatch, your neural network is basically stuck trying to learn in an extremely low signal-to-noise ratio regime, a terrible SNR for almost the entire diffusion trajectory.
Yeah, if you chart out the log SNR trajectory under linear interpolation, having a target variance of 0.12 shifts the entire learning curve downward by roughly 20 decibels compared to a properly variance-aligned setup.
20 decibels is massive.
It's huge. The model is simply overwhelmed by the background noise. It makes it nearly impossible for the network to recover fine-grained waveform structures.
And that causes problems during generation too, right?
Oh, absolutely. Furthermore, at inference time, if you're trying to transport unit Gaussian noise to a low-variance waveform distribution, the math amplifies minor prediction errors. That results in the audible background hiss and static artifacts that have plagued previous audio diffusion models.
So how do you fix it? Because you obviously can't just artificially delete all the natural silences from the audio data set to pump up the variance. You'd ruin the speech data.
No, you can't do that. They used a fix that is incredibly elegant in its simplicity, honestly. Before training even begins, they just multiply the target waveform by a constant scaling factor, which they denote as K.
Just a simple multiplier.
Yep. For the Amelia dataset, they found that setting K equal to 9 works perfectly.
Right, because 9 multiplied by 0.12 brings the standard deviation of the audio up to roughly 1.0.
Exactly. They perfectly align the variance of the signal with the variance of the noise. The neural network trains to predict this scaled-up, louder waveform.
Okay, but then when it generates the audio, it's going to be way too loud.
Well then, during inference, once the model predicts the generated waveform, they just apply the inverse scaling factor. They literally just divide the output by 9 to recover the audio in its original natural amplitude range.
Wow. It's a mathematically trivial operation, but it completely smooths and balances the signal-to-noise trajectory. It allows the model to actually hear the signal over the noise.
It really is always the simplest scaling tricks that unlock the biggest breakthroughs in deep learning.
Totally agree. But they didn't stop at variance alignment, did they? They also took a hard look at the training schedule and fundamentally altered it.
Yeah, the second major training trick is noise-shifted temporal scheduling.
Okay, what does that mean in practice?
So traditionally, flow matching models sample their training time steps uniformly from 0 to 1. But with the X prediction objective, the difficulty of the task is highly imbalanced across that timeline.
Right, not all time steps are equally hard to learn.
Exactly. When you are at time step 0.1, which is near pure noise, reconstructing the global waveform structure is incredibly hard. But when you are at time step 0.9, near the clean data, it's just a matter of minor denoising.
So if your training loop samples those time steps uniformly, you are wasting incredibly valuable compute what we call number of function evaluations, or NFEs on the easy stuff.
Exactly. You are over-optimizing the simple denoising while under-training the complex structural generation.
So how do they shift it?
To fix this, instead of a uniform distribution, they sample their training time steps from a logit normal distribution with the mean heavily shifted to -0.8.
-0.8.
Yeah, in practice, this skews the sampling density heavily toward the high noise regimes. It forces the model to spend the vast majority of its optimization capacity on the early high noise stages.
Because that is the critical phase where the coarse linguistic structures, the prosody, and the text-to-speech alignments are actually formed.
You got it. It prevents the network from wasting time on redundant near-clean denoising.
Okay, let's synthesize where we are for a second. They stabilize the target math with X prediction, they scale the variance so the model can actually perceive the signal over the noise, and they schedule the time steps to heavily focus the compute on the hardest parts of the generation trajectory.
That's the core of it, yeah.
But even with all of those optimizations, mapping pure random noise to high-dimensional raw waveforms contains an insane amount of microscopic redundancy. Which brings us to a part of the paper I really want to challenge you on.
Oh, I think I know what's coming. You're referring to the Perceptual guide they introduced.
Yes, the multi-scale mel-spectrogram loss. When I was reading through the methodology, I hit what looked like a massive contradiction.
It does look like one at first glance.
Because the entire premise of this deep dive, the core insight we gave you listeners at the very beginning, is that WaveTTS is completely ditching mel-spectrograms. But then they use a quote-unquote multi-scale mel-spectrogram loss during training. Isn't that cheating?
I get why you'd say that.
Doesn't that completely defeat the purpose of calling this direct raw waveform modeling?
It definitely sounds like a contradiction on the surface, but there is a crucial architectural distinction to make here. The mel-spectrogram is not being used as an intermediate representation.
Okay.
The model strictly ingests raw waveform patches, and its final output is strictly raw waveform patches. The text conditions never interact with a mel-spectrogram space.
So the model itself is truly raw to raw.
Yes. The mel-spectrogram is strictly used as an auxiliary loss function to guide the gradients during training. That's it.
Unpack how that works mechanically. How do you apply a mel-spectrogram loss if the model isn't outputting a mel-spectrogram?
This is where the X prediction objective becomes incredibly powerful because the model outputs the full, clean, raw waveform at every single training step rather than just a velocity vector. The researchers can easily take that predicted waveform, run a standard Fourier transform on it in real time, and extract the log mel-spectrogram.
Oh, I see.
Yeah, and then they just compare that predicted spectrogram to the ground truth spectrogram across 7 different time frequency scales.
So they're basically penalizing the model if the broad acoustic frequencies don't match up, but the neural network itself is still only generating pure raw audio patches.
Exactly. And they just weight this auxiliary loss very lightly in the overall optimization equation with a lambda of 0.05.
So it's just the gentle nudge.
Right. The reason this auxiliary guidance is so necessary is that relying solely on time domain flow matching forces the model to fit perceptually insignificant sample level variations.
What does that mean for the listener?
Well, the model tries to get the exact microscopic wave shape perfectly right mathematically, even if the human ear literally cannot tell the difference between 2 different phase alignments.
Oh, so it's wasting parameter capacity on phase variations that simply don't matter to human perception.
Exactly. By adding this auxiliary perceptual loss, they force the model to capture global spectral structures like phone pronunciation and broad intonation alongside the local acoustic details.
That makes total sense.
And the impact of this specific loss function is staggering. In their ablation studies, they found that without this mel-spectrogram loss, the model wastes so much capacity on microscopic noise that it struggles to generate intelligible speech efficiently.
Wow.
But with the loss applied, training convergence skyrockets. The word error rate, or WER, drops below 5% at just 200,000 training steps.
That is an insane speed up for a sequence model of this size. It's like giving a calculus student the answer key to periodically check their work while they're still learning the complex formulas. They learn the underlying mechanics 100 times faster because they have a guidepost.
That's a perfect way to put it.
Now, with the training pipeline fully dialed in, we need to look at how this model actually behaves in the real world. How do you sample from this model at inference? And does all this architectural tuning actually pay off when you run it against the industry benchmarks?
Well, at inference time, you have to solve the ordinary differential equation, the ODE, to transport your initial random noise into a coherent speech waveform. But the researchers found that standard inference schedules just weren't cutting it for raw audio. In ODE integration, early-stage truncation errors in the high noise region are fatal.
Fatal how?
If your solver makes a numerical error at the very beginning of the generation trajectory, it permanently destroys the global waveform structure. You end up with garbled noise, and the model cannot recover the speech later in the process.
So you need to aggressively pack your integration steps into the very beginning of the generation process to make sure that foundation is rock solid.
Yes. They solved this by introducing PolyShift inference scheduling. It combines a polynomial transformation with a time shift function.
Okay, some heavy math there.
Yeah, but by setting the power factor to 2 and the shift factor to 3, they dynamically allocate a very dense cluster of time steps early on in the high noise region.
And that works better.
Much better. This drastically outperformed previous dynamic scheduling methods like sway sampling, which simply didn't shift enough compute to the early stages to handle the high-dimensional demands of raw audio.
And the results on the benchmarks are pretty undeniable. I mean, they tested WavTTS on the 100K hour Amelia dataset, evaluating it on the TTS English test set.
Yep.
The model achieves a 1.50% word error rate and a 3.92 UTMOS score for naturalness.
To put that achievement into context for the field, WaveTTS absolutely crushes prior end-to-end models like VITs and JETs.
Those are the previous gold standards, right?
Yeah, but VITs and JETs are often marketed as end-to-end, but under the hood, they still rely on lower resolution latent spaces and adversarial decoders. WaveTTS operates natively in the raw space and easily beats them.
That's incredible.
And more impressively, it goes toe-to-toe with the absolute best latent diffusion models currently available, like F5 TTS and Mask GCT.
So it is matching state-of-the-art zero-shot quality without using any codecs or vocoders.
Exactly.
But looking at the ablation studies, there is a significant catch regarding data scaling. This isn't a lightweight architecture you can just train on a small data set, is it?
No, definitely not. Raw waveform modeling is extremely data hungry.
How hungry?
Well, they tried training WaveTTS on the standard LibreTS dataset, which contains about 585 hours of speech. The model completely failed to capture zero-shot speaker similarity.
So it couldn't clone voices.
Right. It could generate intelligible speech, but if you gave it a 3-second prompt of a voice it had never heard before, it couldn't clone that voice effectively. The massive jump to the 100,000-hour Amelia dataset was strictly required to unlock that zero-shot capability.
Which makes sense physically if you think about it.
Yeah.
Because raw audio contains so much uncompressed detail, ambient room noise, microphone acoustics, microscopic phase differences. The model needs a massive distribution of data to figure out what actually constitutes the target speaker's unique timbre versus what is just random background noise in the prompt.
Exactly. You need large-scale data and matched model capacities to navigate that high-dimensional space effectively.
Did they try any other representations?
They did. The researchers also tested flow matching on other lossless representations to see if they were better alternatives to raw audio. They tried STFT, the short-time Fourier transform, and MDCT, the modified discrete cosine transform.
And both of those are frequency domain representations that don't lose data like mel-spectrograms do.
Right.
So what happens when you try to apply flow matching to those lossless frequency spaces?
MDCT failed dramatically. The mathematical nature of MDCT results in a featured distribution that has a tiny standard deviation overall, but extreme astronomical outliers.
Oh, a neural network hates that kind of variance.
It does. It makes it an absolute nightmare for flow matching to optimize. Now, STFT technically worked, but it converged incredibly slowly. With STFT, you have to model complex valued coefficients, meaning the network has to learn the intricate coupling between magnitude and phase structures simultaneously.
So direct raw waveform modeling wasn't just better for audio quality, it was actually mathematically simpler to optimize once they fixed the variance scaling and the time step scheduling.
That is the beauty of this research. Raw audio is the most ground truth representation of sound we possess. WaveTTS proves that if you handle the noise trajectory correctly, the simplest, most direct representation of the data is often the most powerful.
Which brings us to the bigger picture. We've gone through the mechanics, the patchification, the X-prediction, the variance alignment, the PolyShift inference scheduling. What this means for you, the ML engineers building these systems, is that the AI community can officially stop relying on the crutch of vocoders and neural codecs for high-quality audio generation.
Totally. Raw waveform flow matching works, and it scales.
If we expand on that technical victory, I want to leave our listeners with a final, broader paradigm to ponder.
Okay, let's hear it.
If we can successfully patchify and diffuse raw audio at 16 kilohertz using a standard diffusion transformer, what does this mean for the next generation of native multimodal models?
Oh, that is a massive implication because the entire industry is currently racing toward multimodal architectures.
Exactly. Historically, we have forced continuous signals like audio and vision into discrete tokenizers just to make them play nice with the text processing architectures in large language models.
Right.
But if intermediate representations and discrete tokenizers aren't strictly necessary for high-fidelity audio generation, we might be on the precipice of foundational models that entirely ditch discrete tokenization.
Imagine a single unified flow matching framework that directly ingests and generates raw, uncompressed, continuous sensor data.
Audio waveforms, video pixels, even continuous robotic proprioception data, all processed in their native continuous states without ever being compressed into a lossy JPEG equivalent. WavTTS proves the underlying math scales. It proves we are finally ready to stop hallucinating the pixels and just edit the raw file directly.